Hello everyone! In this lesson, we will continue to learn the frequency domain analysis module of continuous system. Today, we will study the spectral characteristics of typical aperiodic signal. Typical aperiodic signals include rectangular pulse that you have learned in the first knowledge module, unilateral exponential signal, DC signal, sine function, raised cosine pulse signal, and a sampling function. To begin with, let's look at the rectangular pulse signal. This is the time domain waveform of the rectangular pulse signal. According to the definition of Fourier transform, we can find its spectral density function. Finally, we can get its spectral density function as shown in Formula 1. Here, you can find that spectral density function of the rectangular pulse signal changes according to the law of sampling function. This is its amplitude spectrum as shown in Formula 2, and this is its phase spectrum as shown in Formula 3. Let's take a look at its spectrum. Figure 2 is the spectrum of a rectangular pulse signal. Figure 3 shows its amplitude spectrum, and Figure 4 shows its phase spectrum. We can regard its first zero crossing point as its frequency bandwidth, represented by 2 pi over tau or 1 over tau. Let's look at unilateral exponential signal. The time domain waveform of unilateral exponential signal is shown in Figure 5. According to the definition of Fourier transform, we can get the spectral density function of unilateral exponential signal as shown in Formula 4. Figure 6 is the amplitude spectrum of a unilateral exponential signal, and Figure 7 shows the phase spectrum of a unilateral exponential signal. Now let's take a look at DC signal. Figure A shows the time domain waveform of the DC signal. Obviously, it is not absolutely integrable, so we cannot find Fj omega according to the definition. But we can make a transformation. Figure 8 is a rectangular pulse signal. When tau approaches infinity, the rectangular pulse signal approaches such a DC signal. So we can find the spectrum of DC signal through the way of finding the limit as shown in Formula 5. Figure 10 is its spectrum. Obviously, the spectrum of DC signal changes according to the law of impulse function. But what is its physical meaning? Obviously, the frequency band of a signal with infinite time domain width becomes infinitely narrow. In special cases, when E equals 1, the Fourier transform is 2 pi delta omega as shown in Formula 8. As for the derivation of spectral density function of DC signal, you can learn it after class. Let's move on to sine function. This is the mathematical model of sine function, and this is its waveform. Obviously, the sine function is not absolutely integrable. We can make a bilateral function. In such a bilateral exponential function, when alpha approaches 0, this bilateral exponential function approaches to be a sine function. According to the definition of Fourier transform, we can get the Fourier transform of the sine function. Its spectral density function is 2 over j omega. Let's look at its spectrum. This is its amplitude frequency characteristic. Obviously, it is an even function. And this is its phase frequency characteristics. It is an odd function. Let's look at raised cosine function. This is its time domain waveform. According to the definition of Fourier transform, we can get the spectral density function of the raised cosine pulse signal, as shown in Formula 7. In order to describe its amplitude-frequency characteristics, we can transform its spectral density function into Formula 8. It can be found that the spectrum of raised cosine pulse signal is more intensive than that of rectangular pulse. Its mean frequency is concentrated within 2 pi over tau. Finally, let's look at the sampling pulse signal. Formula 9 is the spectral density function of the sampling pulse signal. Obviously, it changes according to the law of the gate function. Figure 15 shows the time domain characteristic of the sampling pulse signal. Figure 16 shows its frequency domain characteristics. Here is a question for you. For sampling signal, what is its frequency bandwidth? And what is its maximum frequency? In the first knowledge module, you have learned that the sampling function can be described by sinc t. That is to say, it can be expressed as sin pi t over pi t. If the sampling signal is represented by this mathematical model, what does its spectrum look like? Please find its corresponding spectrum according to the change mode of sampling signal after class. Let's make a summary for the contents of the frequency spectrum of typical aperiodic signals. First, we discussed spectra of the rectangular pulse signal, unilateral exponential signal, DC signal, sine function, bilateral exponential signal, and a sampling function. You should know that the frequency spectrum of rectangular pulse signal changes according to the law of sampling function. The frequency spectrum of DC signal has the characteristics of impulse function. The frequency spectrum of sampling function signal changes according to the law of gate function. Actually, in the basic knowledge module, we also discussed the impulse signal. As for the time domain characteristics of step signal and the impulse couple signal, they are all special singular functions. We will discuss their frequency characteristics in the next lecture. This class is over. Thank you. Goodbye.